This is A4 paper, folded in half to get A5. Wrong! Actually, A4 is defined as 210 times 297 millimeters, and A5 is defined as 210 times 148 millimeters, which means that two A5s together have a tiny 1 millimeter strip missing from being one A4. If you're anything like me, you find this extremely annoying. But it gets worse. Here's a question that sent me down a deep mathematical rabbit hole and accidentally produced some really pretty proof pictures. How many sheets of A10 fit into one A0? A10 is the smallest paper size defined in ISO 216, which is the standard that almost all countries use, except America and the Philippines. A10 is this, and A0 is this. Divide the area by both to get 1039.4? This is a funny number, because you would expect to get 1024, which would be 2 times 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 2 as you fold in half each time. This is because of a rounding error introduced by rounding down to whole millimeters. Anyway, so that means that 1039 sheets of A10 fit into one A0, right? No. Just because 1039 fit in by area doesn't mean you can actually arrange them side by side to fit into each other. So the actual relevant question, I think, should be, how many A10s can you cut out of a single sheet of A0? So, of course, I made a little website where you can try. For now, assume you can only cut vertically and horizontally. Appropriately, I called this website Fun Orthogonal Rectangle Packing, or FORP for short. So I played around with this website a lot and constructed this pattern. This is an arrangement of 1038 sheets of A10 fitted into one A0. I then tried finding an arrangement for 1039 for about a week, and I couldn't. It just didn't seem to fit. Every time I got 1038, the last one just didn't quite fit in. So I had to do a bit of research. Unfortunately, I couldn't really find anyone answering this question directly. Fortunately, this problem of placing identical orthogonal rectangles into one bigger, larger rectangle has a name. It's the padded loading problem, or PLP for short. The PLP turns out to be quite useful in logistics, especially when loading shipments into containers. So a lot of people did a lot of research and spent a lot of time working on really smart algorithms, which is great. So I found this really good paper on a really good algorithm. I downloaded the code. I asked the authors for help because I had problems running the code. Got help from an author. Thanks, Rafael Lobato. And he ran his really good algorithm and it produced another layout of 1038 sheets of paper. But does that mean that 1039 is just not possible? I think that's a really good question. And trust me, this is a question that will lead to some really, really good pictures at the end. The obvious idea is to just try out all arrangements. However, that's simply just not possible. There's just way too many possible arrangements. However, one could maybe hope for a fast algorithm that provably produces the optimum result every time. Well, no. Research has shown that the PLP is NP-hard, which basically means that if we had a quick algorithm for solving the PLP optimally, then we'd also have a quick algorithm for solving a lot of problems that we strongly believe to be very hard. So probably there doesn't exist a quick algorithm. Thus, the strategy of just trying all arrangements won't work. We probably need to do something smarter. Obviously, a lot of people have already come up with strategies for disproving and proving certain upper bounds for the padded loading problem. Unfortunately, they all just don't work because this instance is just very ugly numerically. If you want the gory details, I'm writing it up as a paper and we'll be linking it in the description once it's finished. So that means that we need to do something in between, something that's not super smart, but also not just trying out everything. To help understand my proof, I first want to show you a famous Olympiad puzzle. Consider an 8x8 chessboard. How many 2x1 dominoes can be placed onto the chessboard? Well, place 4 of them in each row. So but now, remove 2 opposite corners. How many can you place now? Well, here's a clever argument. No matter where you place the domino, it always covers exactly 1 white square and 1 black square. We removed 2 white squares, so there's only 30 remaining white squares. So 31 dominoes can't be placed, no matter how hard you try, but 30 is possible as we saw before. So 30 is in fact optimal. Let's apply this argument to a big rectangle, put a weight on each one of the approximately 1 million pixels, and ensure that each possible rectangle covers at least a weight sum of 1. Let's maybe also color the pixels based on how much weight we assign to them to make it a pretty picture. If we find such a coloring of the A0 grid with a total weight of something strictly less than 1039, then that would exactly prove that 1039 A10s cannot fit into one A0. So how do we find such a coloring? If you haven't noticed, this is a moment where finally the pretty pictures make an entrance. Let's first try the simple coloring, a uniform one. Let's assign each pixel a weight of 1/962, since each A10 rectangle covers exactly 962 pixels, no matter if we lay it vertically or horizontally. We can check and find out that indeed, under this uniform coloring, every rectangle covers exactly weight 1. The total weight of this image is 1039.4, which is a familiar number. It's the area upper bound we got earlier, which makes sense if you think about it. As a reminder, we're trying to find coloring such that the total weight is below 1039, because that would prove that an arrangement of 1039 A10s in an A0 is not possible. Here is a little bit more advanced pattern. I gave each row and column a weight and then calculated the weight for each pixel to be the sum of the column and row weight. Then I wrote some clever code to compute the optimal row and column weights to minimize the total sum, and got a total sum of 1039.0254. That's really close to being below 1039, but not enough. It does, however, give us a pretty image of the weights. So why not just let my computer find optimal weights for the entire A0 directly? Assign each pixel a variable, express the sums of each rectangle as linear constraints, and then tell the computer to minimize the total sum. Oops, that's just one very large linear program. If you don't know what that means, don't worry. It's just this kind of linear optimization problem that is very common and surprisingly easy to solve, that people have developed some really fast algorithms to solve these. Still, a problem of this size would require a lot of computation. Luckily, my university gave me access to a lot of computation. So I was able to give it around 500 gigabytes of RAM and about a week of compute time, and it produced this optimal coloring. And here it is! This coloring has a total weight of 1038.73. That's strictly below 1039, so this proves that 1039 is not possible. Thus, this proves that this packing of 1038 sheets is indeed optimal. Yippee! But wait! Don't you also think that that weighing pattern looks like really cool? Same, and I think it's really beautiful, and it's also like super cool that it's essentially a mathematical proof that 1039 is indeed not possible. Anyone can verify it by just computing the sum of all possible rectangles in about 5 lines of code. Okay, so I had a bunch of fun, and I produced a lot more of these optimal weight images for a lot of different instances of the palette loading problem. This, for example, is the optimal coloring for when the big rectangle has size 64 x 64 and the small rectangle has size 9 x 2. It has a total weight of 227.5, which doesn't really mean anything for us right now, but the important bit is it's really beautiful. Anyways, so I did the obvious. I made yet another website. I called it the Gallery of Papel. And it houses all of these images for all possible rectangle sizes up to and including 64. The gallery thus contains over 40,000 images, each the mathematical optimum, within floating point precision, of course. There's 64 floors, so you probably find one that no one has ever really looked at. Most are pretty boring, but there are some really nice patterns in here. Text me if you ever need inspiration for your new carpet. Also, I added the ability to write comments on images for fun, if that helps. By the way, if the design of a website looks familiar, that's because I copied the code from an old project of mine, a previous 3D website I made. Link is here. Okay, that was the video. I hope you enjoyed it. I left out a bunch of really interesting maths on finding like optimal weighing patterns. For example, the question of this proof method of always finding the optimal coloring being universal or not. So if it always produces the optimal upper bound. You'll find these details in the paper I'm going to finish over the next few weeks. I will link it below. I hope you enjoyed this little mathematical rabbit hole of A4 paper sizes. I thought about including like a bit more about history behind A4 paper, but I thought I would just focus on the maths and the important bits and bobs. Links to everything, including the FORP website, the gallery, the future paper, and whatnot will be in the description. Thanks for watching, I guess. Bye.